Welcome. This is Team Transformers, and the title of our project is called Acoustic-Based Multilingual RoBERTa Language Model. So the game plan of today is that I'm going to walk you through our problem statement, present you with our task and methods before showing you our results and conclusions. So our project is built to aimed to build a multilingual audio-only spoken language understanding system. It can reduce information loss or error that's coming from the automatic speech recognition system. ASR know that does not work well for low-resource languages. So our project can be applied to the real world by extending it to low-resource languages because our flexible input format. And it can also enable devices such as multilingual voice assistant who can respond correctly to instructions such as take me to Longmen-Kejian. So there has been previous work done in this area. The state-of-the-art use Allosaurus to replace the ASR and then using a model that's based on CNN and LSTM. And in our work, we replaced the baseline model with RoBERTa, and this is actually the first attempt that used BERT-based model on phonetic transcription. So as I just talked about, we implemented a novel approach using RoBERTa, and we also re-implemented a state-of-the-art model based on CNN and LSTM as our baseline, whose structure can be shown as shown in the picture on the right. We also, for a data set, we configure one Chinese and one English spoken language understanding data sets for intent classification, respectively. So we first pre-train our RoBERTa model on one Chinese and one English speech corpus, and then we fine-tune the model on our configured data sets.
Now let's talk about data sets. In our system, there are 3 stages to require the use of datasets: pre-training stage, fine-tuning stage, and the downstream task. We selected 2 datasets to pre-train the model using masked language modeling, one for English and one for Chinese, respectively. The English corpus contains 100 hours of natural speech data in dot wave format, and the Chinese corpus contains approximately 80 hours. After pre-training, we fine-tuned the model and trained it to perform intent classification with another 2 datasets, SNPs for English and CAT-SLU for Chinese. Both intent classification datasets contain speeches to some smart devices, such as Smart Light and Smart Assistant, and each piece of smart speech file in these datasets has been labeled with an intent. Here are 2 examples. For the Chinese dataset, you may have a wave file saying 帮我导航一下盘龙城, which means help me navigate to Dragon City in English. And you also have access to the label of the intent, which is 0 in this example. Then in our system, we would first transform the wave file into a list of phonetic symbols and train the model to output 0, which is the very first class of this dataset, and it means bringing out the map. Similarly, in the English dataset, we may have a speech saying, can you please change the light color to pink? Then we would do the same work, first transform the wave file into a list of phonetic symbols, input it to our model, and expect the model to output 4, which is the label for setting color.
Here is the illustration of the pipeline. The input is an audio file in wave format. The audio file has utterances like, can you please change the light color to pink? Which is then converted into international alphabet transcript of audio. The RoBERTa model then takes in transcript to classify the intents. Here is an overall comparison of our SLU pipeline against traditional SLU pipeline. In the past work, a speech-to-text module will convert spoken utterances into textual transcript, which is then fed into a natural understanding module to perform downstream task. In our work, however, we replace the speech-to-text module with Allosaurus that generates language-independent phonetic transcript. The phonetic transcript is then fed into RoBERTa for downstream tasks, such as intent classification.
This is the illustration of our model. We use RoBERTa, which is a transformer-based model and can learn a relationship between words simultaneously compared with normal LSTM. And the values of the related hyperparameters of RoBERTa are listed below. We found that our method has varying performances on the 2 datasets. For the Chinese datasets, our RoBERTa method outperforms the baseline model. However, for the English datasets, our method has slightly worse performance than the baseline model. One possible reason we think is that the English datasets has more classes than Chinese, so the average number of English training instances per class is less than that of the Chinese training set. A BERT-based model with more parameters than the baseline model may require more training examples to gain a deep understanding of the input phonemes and the underlying task. We also trained a multilingual language model using both English and Chinese datasets, but found that it has worse performance, which is likely because the 2 datasets have a different set of intent labels. In summary, we propose a novel acoustic-based SLU system based on RoBERTa. This is the first attempt that applies BERT-based model on phonetic transcript. We test this system on 2 new datasets that are in Chinese and English respectively. We found our system achieve competitive results with the state-of-the-art model. Future work could include testing this system on the larger datasets and on low-resource languages.